Welcome all. In this video, we are going to talk about polynomials solvable by radicals. Basically, radical means a root, or in general, we may call it as a nth root. Okay, we know that quadratic polynomial, cubic polynomial, or quartic polynomial can be solved by a formula which contain roots. So all these polynomials are solvable by radicals, but polynomial of degree 5 or more than degree 5 cannot be solved by radicals, which is our prime target of this video. Now, let us look at an instance. So for that, I will consider a quadratic polynomial. So suppose polynomial is ax square plus bx plus c equal to 0. We know that roots of this polynomial can be simply given as x equal to minus b plus or minus square root of b square minus 4ac divided by 2a. Now, in this particular formula, square root of b square minus ac is a square root of b square minus 4ac. So it is nothing but a radical. So that means this particular polynomial can be solved by radicals. Same is the case with cubic and quartic polynomials because they also have formula to find their roots which can contain roots or radicals. But that is not the case with the polynomials of higher degree. So to prove that, we will require some fundamental concepts. So to deal with proof of that theorem, so we will start with one definition, that is definition of cyclic extension. So let's start with a definition of cyclic extension. So an extension k over f is said to be cyclic if it satisfies two conditions. First, that it is Galois extension. So k over f is Galois extension. And secondly, its Galois group should be a cyclic group. So secondly, its Galois group should be cyclic. So an extension which satisfies these two conditions is called as a cyclic extension. Now we will have an example to illustrate this idea. So for that, we will consider an extension of q root 2 over q. It is easy to identify that Galois group of q root 2 over q has two automorphisms, identity and sigma, where sigma maps root 2 to minus root 2. So let's write, so Galois group of q root 2 over q is equal to identity and sigma, where sigma is automorphism which maps root 2 to minus root 2. Now let's try to find out that this particular extension is cyclic. It's quite obvious that this extension is Galois extension because degree of extension is 2 and number of automorphisms is also 2. So cardinality of automorphisms of q root 2 over q exactly matches with the degree of extension of q root 2 over q, and that is the reason this extension is Galois. So let's try to identify that this Galois group is cyclic so that this extension will become cyclic. For that, what I will do, I will take the powers of sigma. So firstly, sigma raised to 1 is sigma. Let's try to identify what is sigma square. So sigma square, to identify sigma square, we will take a random element, say sigma square of a plus b root 2, where a plus b root 2 is a random element of q root 2. So that is equal to sigma of a plus b root 2. Sigma is automorphism of q root 2, it fixes q. So definitely when sigma is applied on this element a plus b root 2, we will have a plus b and sigma of root 2, but sigma of root 2 is minus root 2. Again, when we will apply sigma on this, we will have sigma of a equal to a because a belongs to q, it is fixed. Sigma of b equal to b is fixed. Okay, and sigma of minus root 2, okay, that is minus, again minus of root 2, so that is root 2. So you'll find that sigma square of a plus b root 2 is a plus b root 2, so that is same element. So this clearly indicates that sigma square is identity automorphism. So sigma generates a complete Galois group. So that's why this particular Galois group is cyclic. This extension is Galois extension. So that is why this particular extension is a cyclic extension. Now we will extend these ideas further and we will state and prove one proposition. Proposition says that, so let me first of all write down the statement of proposition. It says that let F be a field such that characteristic of F does not divides n. Okay, and it contains it contains the nth roots of unity. The nth roots of unity. Okay, we have to prove that. Then the extension say F nth root of a, nth root of a is attached to F, where a belongs to F, is cyclic over F. Okay, and its degree of extension does not divides n, and degree of extension of F nth root of a over F does not divides n. So let's try to establish the proof of this result. Proof is quite simple. First of all, let us abbreviate f nth root of a as k. So let k equal to f nth root of a. Okay. After that, f contains all the nth roots of unity, right? So definitely it's quite obvious that f nth root of a contains all the roots of polynomial x raised to n minus a, because if I will put x equal to nth root of a, it is not difficult to understand that it satisfies a polynomial x raised to n minus a equal to 0. So if we'll consider this polynomial x raised to n minus a equal to 0, okay, then all its roots will be in f nth root of a, because f contains nth root of unity. So that's why this particular extension contains all the roots of this polynomial, and basically all the roots of this polynomial are distinct because nth root of unity are distinct. So that's why this is separable polynomial. Okay, to be more specific or to be more clear, we can say that roots of this polynomial are a raised to 1 upon n, then a raised to 1 upon n, say xi, then a raised to 1 upon n, say xi square, so on a raised to 1 upon n, say xi raised to n minus 1, where xi is nth root of unity, primitive nth root of unity, and xi square, so on xi raised to n minus 1 and 1, all are the nth roots of unity. All these roots are distinct, so that's why this polynomial is separable. Okay, and k, which is f nth root of a, contains all these roots, so that's why k becomes splitting field of this polynomial, and splitting field of separable polynomial is Galois extension. Okay, so that's why k becomes Galois extension of f. So clearly k is Galois extension of f. You may write a reason in bracket, because k is a splitting field of a separable polynomial x raised to n minus a over f, because it contains nth roots of unity. That's the reason k becomes Galois extension of f. Okay, now we will work on Galois group. Okay, so because we want to prove that Galois group is cyclic, so we will work on Galois group now. So let's first of all consider some random element from Galois group. So let sigma belongs to Galois group of k over f. Okay, now nth root of a is a root of x raised to n minus a equal to 0. Then sigma nth root of a is also a root of x raised to n minus a equal to 0. So clearly sigma of nth root of a is also a root of x raised to n minus a equal to 0. Okay, so this nth root can be written as sigma nth root of a can be written as equal to, just say, xi sigma into nth root of a, where xi sigma it becomes nth root of unity. So where xi sigma is nth root of unity. So what happens? This establishes a map or say correspondence between Galois group and nth roots of unity, because when we took sigma from Galois group, we obtained nth root of unity, that is xi sigma. Okay, for sigma. So definitely this particular correspondence can be written as, so there is a map. So there is a map, say F, between Galois group of K over F and say nth roots of unity. Mu n is a set of all nth roots of unity. Okay, and it is defined as f of sigma is equal to xi sigma. That's a map. Okay, so what happens? This clearly indicates that all the roots of unity are in field F. Okay, because every nth root is contained in F, right? So that's why we can easily find what happens. Is it a homomorphism? Because if we will able to prove that it is injective homomorphism, then definitely Galois group is contained in mu n and mu n is cyclic. So subgroup of cyclic group is cyclic, so that's why Galois group will become cyclic. So we only need to prove that this particular homomorphism, this particular map is injective homomorphism. Okay, so let's try to establish that fact. First of all, what I will do, I will try to identify what is a sigma tau of say nth root of a. So I'm trying to establish that it is homomorphism. So that is equal to sigma of tau of nth root of a, but that is equal to sigma tau of nth root of a is nothing but xi tau into nth root of a. So xi tau comes out, this is sigma of nth root of a, and that is equal to xi tau xi sigma into nth root of a. But mu n is a cyclic group, it is abelian as well, so that's why we may write it as xi sigma into xi tau nth root of a. So image of sigma tau is xi sigma xi tau. So xi sigma xi tau, let me just correct it, it is xi sigma xi tau. So that is equal to xi sigma means f of sigma, xi tau means f of tau. So image of sigma tau, f of sigma tau is f of sigma into f of tau, so it is homomorphism. Okay, now we will work on kernel. What will be kernel of f? So kernel of f means set of all automorphisms, okay, which fixes nth root of a. But set of all automorphisms which fixes nth root of is only identity map. Okay, so kernel of f is only singleton identity, because nth root of a should be fixed. Okay, and that can be done by only identity map. So kernel of f is singleton identity, so that is the reason that this is injective as well. So f is injective homomorphism, so thus f is injective homomorphism. Okay, that is embedding, and that's why Galois group of K over f is contained in mu n. Okay, it is itself a group and it is contained in mu n, that means it is a subgroup of mu n, and mu n is cyclic multiplicative group of nth roots of unity. So this implies Galois group is also cyclic. So this implies Galois group of K over f is cyclic. You may mention a reason here, because mu n is cyclic. Okay, so in this way we can prove that if we attach nth root of a to a field f with characteristic of f not dividing n, then definitely that is going to be cyclic extension of f. Okay.
Let us now talk about polynomials soluble by radicals. But first of all, we'll try to understand what do we mean by element soluble by radical. So suppose we are provided with an element over a field F which is algebraic. Okay. So let me consider that element. So suppose alpha is an element given to us and this alpha is algebraic over F. Fine. Okay. Now I can say that alpha is soluble by radicals, or expressed by radicals, or we can say that it is solved for in terms of radicals if the following is satisfied. So alpha is said to be solved by radicals if alpha is an element of field K which can be obtained which can be obtained by a succession of simple radical extensions, by succession of simple radical extensions, that is f equal to k naught, say, and alpha is algebraic over f, so we should be able to find field k1 that is contained in k2, that is contained in so on, contained in say ki, ki is contained in ki plus 1, ki plus 1 is contained in so on, and finally that particular sequence ends at ks equal to k, and each of these extension is a simple radical extension. That means k1, or in general we may say ki plus 1, is nothing but it is obtained by attaching nth root of ai to previous field ki. So ki plus 1 is nothing but ki attached with nth root of ai, obviously where ai belongs to ki, where ai belongs to ki. Okay, now in this way we can form a sequence of fields, and we can say that alpha is in a root extension. Okay, so we can say that such extension can be called as a root extension, or such a field can be called as a root extension of f. Now how this is related with the polynomials? So basically polynomial is said to be solved by radicals if each of its root can be solved by radicals. Okay, so idea is quite simple. A polynomial can be solved by radicals if each of its root can be solved by radicals, can be solved by radicals. Okay, so here we'll provide an instance so that you can easily capture the idea. So suppose I'm taking alpha equal to say -1 plus root of 17 plus say root of 2 times 17 minus root of 17, then plus 2 times square root of 17 plus 3 times root of 17 minus square root of 2 times 17 minus root of 17 minus 2 times square root of 2 times 17 plus square root of 17. Now this particular number alpha is used in the construction of 17 gone. Okay, and we'll show that this particular number can be solved by radicals. So first of all we'll start from a field q. Okay, so we will take k naught equal to q. Okay, then we will take k1, so k naught equal to q, then we'll take k1 equal to q, we will attach square root of 17 to it. Okay, so slowly we cover all this. Minus 1 belongs to q, root 17 belongs to k1. Okay, so q root 17, then we will find the next field k2 by attaching to k1 next element, that is square root of 2 times 17 minus root of 17, so square root of 2 times 17 minus root of 17. So this particular element is covered now, and finally we will move to the second last field, that is k3. K3 can be obtained by attaching k2 square root of 2 times 17 plus square root of 17. This is done so that this particular square root is taken care of. Now this is also taken care of, root 17 is also taken care of. Okay, so all these are been taken care of. So we can now finally form K4 by just attaching a square root, a complete square root of this, say 17 plus 3 root 17 minus 2 times square root of 2 times 17 minus root of 17 minus 2 times, say square root of 2 times 17 plus square root of 17, right? So we can easily observe that first of all we started with q naught, that is k naught. Then we started with k1, we attached root 17, so we took care of this element. Then we took care of this square root. Okay, now we cannot directly attach this square root because still this root is not taken care of. So firstly we attach this square root to k2, and then after we'll attach a complete square root to k3 to obtain k4. And we can easily find that alpha belongs to k4, right? So that's not difficult task. We can easily identify that alpha belongs to k4. That's why alpha is solved by radicals. Okay, and k4 is nothing but a root extension. Now after this example we will move to an important result, and we'll try to prove that result. Okay, so let me just write that result. Result is something like this. We will let's just call this result as lemma. Result reads like this: suppose alpha is contained in root extension. Okay, then alpha is contained in root extension which is Galois, and where each sub extension is cyclic extension. So the point is that if alpha is contained in root extension, okay, if alpha is contained in root extension, okay, then alpha is contained in Galois root extension, or we can say that root extension which is Galois, root extension which is Galois, and each sub extension is cyclic. Because definitely if you are finding root extension, then definitely we will have a sequence of fields, so each sub extension is cyclic. So let's go for a proof of this particular result. So to prove this, firstly we will understand the meaning of Galois closure. Okay, so let's try to understand the meaning of Galois closure of K. So Galois closure of K is nothing but the smallest field, smallest Galois extension that contains K. Okay, so Galois closure is nothing but a smallest Galois extension of K containing K, containing K. So here we are talking about a field K. So alpha is contained in root extension K, right? So we are already talking about field K. So let me assume that L is Galois closure of K. So let L be the Galois closure of K. Okay, now what will happen? Basically we already know that alpha is contained in root extension K. So K is a root extension, so there is exactly the sequence of fields that as we have talked about. Okay, so let me just highlight that sequence. So this is a sequence of fields which makes K a root extension. So since alpha is contained in root extension K, so K has already been identified with the root extensions. Okay, so L is Galois closure of K. So what can I do? I can take one element from Galois group of K over F, or say L over F. So let me take such element. So consider sigma belongs to Galois group of L over F. Okay, and we'll apply this sigma to the previous sequence of fields. So basically sigma fixes F. So when you will apply sigma to K naught, it's not gonna change. Okay, so it will be F itself. But then after we will have sigma of K1, then it's contained in sigma of K2, contained in so on. It is contained in sigma of Ki, it is contained in sigma of Ki plus 1, and so on. It is contained in sigma of Ks, which is nothing but sigma of K. Okay, so likewise we can obtain a new chain of subfields. Now one simple thing is there here, each and every sub extension is a simple radical extension, because basically Ki plus 1 was obtained by attaching nth root of Ki, nth root of Ai to Ki, right? Now sigma of nth root of Ai will be attached to sigma of Ki. So that's why these extensions, sub extensions will again be a simple radical extensions. Okay, further composite of two root extension is again the root extension. That means if we have two root extensions, then we can form another root extension by using the composite of those two root extensions. Idea is quite simple. See, let me just explain it simple. Suppose we have a root extension, so definitely you have equal to k naught, that contains in k1, that contains in so on, contains in ki, contains in ki plus 1, contains in so on, ks equal to k, right? That's the root extension. And suppose we have another root extension, so let's try to understand that we have k dash. Okay, suppose k dash is another root extension, so definitely f equal to k naught dash, that is contained in k1 dash, contained in so on, ki dash, contained in ki plus 1 dash, contained in so on, ks dash, that is equal to k dash. Okay, so that is another root extension. Now we can combine these two root extensions. Just we have to take care of one thing. First of all, what we will do, we will apply this k1 dash, because k0 dash is quite common. So we'll apply this k1 dash to each and every field here. Okay, so then what will happen, then we will come across a new composite field, and each the extension will be again, individual extension will be again simple radical extension. Okay, then what will we do, then again whatever new fields that are obtained, we will take its composite with k2 dash, and so on. We'll move on further, and finally we'll obtain a root extension which is composite of these two extensions. Okay, so that's simple idea, that we need to just apply this k1 dash to each and every field here. After doing that, we'll apply k2 dash, and so on. We'll continue this process until we apply ks dash. And when you will apply ks dash to ks, we finally will get a composite of these two root extensions, that is again root extension. Okay, so this is the idea. So that's why composite of conjugate fields, okay, is again the root extension, because we started with a sigma belonging to Galois group of L over F. So definitely, let me write that. So composite of conjugate fields, composite of conjugate fields, conjugate fields म्हणजे fields of this kind, sigma of k, because sigma is a element of Galois group. So when you apply sigma to k, you will get a conjugate. Okay, conjugate field. So that's the conjugate field we are talking about, because when you will change sigma, for each and every sigma we will get such a conjugate field. So composite of conjugate fields is again a root extension. So because we have used this idea, so that's why composite of two root extensions is again a root extension. So same idea is applied to conjugate fields. So composite of conjugate fields is again a root extension. So composite of conjugate fields is again a root extension. Okay, now composite of all the conjugate fields is gonna be Galois closure. Okay, so that's why it is going to be L, right? So we obtain that alpha is contained in Galois root extension. Okay, because composite of conjugate fields is again the root extension, and alpha belongs to root extension, but composite of all these conjugate fields is going to be Galois closure. because Galois closure is nothing but the smallest Galois extension that contains K. So when you will take composite of all such conjugate fields, that not gonna beyond the Galois closure, so it's gonna precisely be L. Okay, so that's why alpha. So alpha belongs to L. L is what? L is Galois root extension, because already we have proved that composite of conjugate field is root extension. So L is root extension and alpha belongs to L. So L is Galois root extension. Okay. So alpha is in Galois root extension. Okay. Now let's move to the next idea, that we want to prove that this particular extension L is gonna have a cyclic sub-extensions. So what we'll do it by a simple process. Firstly, we'll take F, right? And then we'll attach all the nth roots of any to F. So let's take F. Let's adjoin, or let us attach all the nth roots of unity to F. Okay. So after adjoining all the nth roots of unity to F, we will obtain a new field to obtain, say, F dash. Now keep in mind that F dash contains all the nth roots of unity, so it's gonna be a Galois extension, because it is going to be splitting field of some separable polynomial, because it contains all the nth roots of unity, and we have discussed this idea in the previous part also. So it's going to be Galois extension. Now what we'll do, we will take the composite of this particular Galois extension F dash with K. K is also Galois extension. So K is root extension. So we have a sequence of fields, and we will take composite of that sequence of fields with F dash. We will have something like this. So firstly we will have F. F is contained in F dash, because F dash is a field obtained by F by attaching nth roots of unity. So that will be equal to F dash K naught. Then it is contained in F dash K1. We are taking composite of F dash with each and every of these subfields. Then F dash Ki, that is contained in F dash Ki plus 1, that is contained in so on. Finally F dash K. Now K is also Galois extension, F dash is also Galois extension. So that's why composite of Galois extensions is Galois extension. So that's why F dash K is again a Galois extension of it. So clearly F dash K is Galois extension of F. Now you can observe the sub extensions here. Now each of the sub extension is gonna be a simple radical extension, because this is appropriate field, this is base field F dash, and it contains all the nth roots of unity. So it's not difficult to attach nth roots of AI. Okay, by choosing element of this field, we'll choose the element of this field, we will attach n1th root of a1 to that field, this field, and we'll obtain F dash k1, and so on. We'll continue like this. So definitely these all the extensions are going to be cyclic extensions, because we have already discussed in the first part of the lecture that the cyclic extensions are of the form f nth root of ai. Okay, so each of these sub extension, further each of these sub extensions are simple radical extensions, right? And further each of these extensions, so this process is nothing but clearly this process is obtained by attaching nth root of ai to each of the previous field. So definitely each of these extension is going to be cyclic extension. Okay, and hence we can say cyclic extensions, and that is what we wanted to prove. So we have established the fact that if alpha is contained in root extension, then definitely alpha is contained in root extension, which is Galois, and not only Galois, each of that sub extension is going to be cyclic extension. Okay, so with this we'll stop in this lecture, but in the next video we are going to talk about a very interesting and very important theorem, then under what condition we can say that polynomial is soluble by radicals. So there is a question here: polynomials soluble by radicals. So okay, so under what condition? What should be condition for a polynomial to be solvable by radicals? Let's see this question, and how polynomials of degree say n greater equal 5 is not soluble by radicals. So we are raising these two interesting questions in this video, and we'll answer these questions in the next video. So stay tuned. Thank you.